In this video, we seek to estimate the temperature of a point on Mars, a 1 square meter area, essentially a 1 square meter area that has the sun directly overhead. We're going to estimate the equilibrium temperature. There's going to be power absorbed from sunlight, and we're going to assume the surface acts like a black body and radiates off power. And when the power being absorbed, I'll call it in, equals the power radiated, I'll call it out, then we'll have an equilibrium temperature set up. The black body formula for the power that's radiated by a black body is Stefan's constant, the area, and then temperature to the fourth power. So if there's more power being absorbed than being emitted, we're going to accumulate energy every second, and the temperature will increase. And it'll increase to the place where the power going out does match the power coming in. So that's our basic relationship. At the Earth, we have 1368 watts per square meter available. But Mars is not at that distance from the Sun. Mars is further away. Mars is at 1.524 astronomical units. So at Mars, we find the power available by dividing by the square of the average distance of Mars orbit. So 1.524 squared. I think you would agree that being further from the Sun, there's not going to be as much power available. The total power output of the Sun is shining over an imaginary sphere around the Sun. And if the sphere is bigger, then that set fixed amount of power coming out of the Sun is divided by a bigger number of square meters. The area of the sphere is larger, and we're going to get a smaller number for this solar constant at Mars. The proper way to do that is to simply divide by the distance to the planet measured in astronomical units, square that value, and you'll get the power available at Mars. Then, at Mars, it's not absorbing all that light, so we'll have to just absorb 75% of that light. 25% gets reflected. So let's go ahead and write down our equation here. This 1368 divided by 1.524 squared, that becomes approximately 589 watts per meter squared. That's the solar constant available at Mars, 589 watts per meter squared. So 589 watts per meter squared. 1 minus 0.25. Again, this is our albedo number, the 0.25. And then we're going to do this for 1 square meter on Mars. So the meter squared will cancel off. And I now have how much power, how many joules per second are being absorbed on the surface of Mars. For the power going out, we're going to assume that Mars rotates rapidly enough that the whole planet has the same temperature. That's actually not a good assumption, but that's what we're going to stick with here because this is just a simple calculation. So if we have a rapid rotation, or we've got a real thick atmosphere that keeps the whole surface all the way around the planet in the same temperature, then we'll have a constant temperature throughout. But 5.67 times 10 to the minus 8 is Stefan's constant. Watts per meter squared, Kelvin to the fourth for its units. Again, doing this for 1 square meter. And then the temperature to the fourth power. And I guess I probably didn't need to include this, as the surface of Mars warms up fast enough that this 1 square meter is going to reach this equilibrium temperature before Mars rotation takes it to the dark side of Mars, and it cools off a lot. So ignore my calculation on rapid rotation. This 1 square meter is going to be close enough. It'll raise temperature to the equilibrium value before it rotates much past the subsolar point. So you should pause now and do this calculation on your own and come back when you've finished. Welcome back. You took 589 times 0.75. You didn't do anything with the 1 square meters. You did divide by Stefan's constant. And hopefully what you came up with is something similar to this. 7.79 times 10 to the 9th is temperature to the 4th power. And if you don't have an arbitrary root on your calculator, we need to take 4th root of both sides. If you just take square root twice, what we really need to do is take the 4th root of both sides. But if we take the square root twice, it's the same calculation. So taking the square root twice, I'll just do it here. Take the square root twice of 7.79 times 10 to the 9th. I find 297 Kelvin is our temperature. If I convert this to first Celsius, I have to subtract by 273. The Celsius number is 24 degrees Celsius. And if I want to convert this to Fahrenheit, I start with my Celsius number, I multiply by 9/5. After I get that result, then I add 32, because the 0 Celsius point is the same as 32 Fahrenheit. So I have to shift by 32 as the last calculation. And do this on your calculator. I came up with 75 degrees. Not quite as warm as Hawaii, but comfortable. But that's only for this 1 square meter. It's not for the whole hemisphere of Mars. It's only for the place where the sun is directly overhead, and just for a short time, because this 1 square meter is going to rotate around in about 12 hours, less than that, 6 hours. It's going to be in the shade, not receiving sunlight anymore, and the temperature drops rapidly. But gives us some hope for possible colonies on Mars. There is still solar energy at Mars, and there is a reasonable temperature for a brief period of the day. Again, assuming quite a few things here, that the surface acts like a black body, the percent reflected is just 25%, but gives us an estimate of temperatures on Mars. What you might call high noon, 75 degrees Fahrenheit. And this has been roughly confirmed by spacecraft that have landed on Mars. I don't know if any of them were directly underneath the sun, but they certainly did get into the 60-degree range for some of their temperature measurements. So ask your instructor if you have questions.